All right, so we're back to the same deal with terrible lighting, but I told you guys I would record videos, and I said that I was going to make two, one for separable equations and the other one for linear equations with the integrating factor. So here we are, looking heavenly, actually pretty terrible, but what can we do? So linear differential equations. So P, I don't know. Linear differential equations. So first order, I should say. First order linear differential equations. So let's put here as if I didn't forget. First order. So these are the ones that, from all the differential equations, these are probably the ones where we actually have the most clear and the nicest way to actually solve them. It just happens to be pretty beautiful. And it works in this way. So if you have an equation, linear, first order linear differential equation, so you have a coefficient that depends on x and then some other coefficient q of x or some other function. So what you can do is multiply everything times e to the integral of p of x dx. Lowercase, I changed to uppercase somehow. And the reason why you would do that, e to the integral, and this is called the integrating factor, by the way, that we will just call if. And the reason why it works that way, I'll explain after I finish writing everything. Dx, p of x, y equals, and then e, I should have just called it something and not have to write it over and over, q of x. Okay, this is the same integral, right? So the reason why we do that is because you can verify that if you grab y and you multiply it times e to the integral of p of x dx, and you take a derivative, then by the product rule, you will get precisely that. So let's take a look. So you take the derivative of the first guy, this one, you obtain this. Multiply times the second, so you get this term. So your first term for your product rule gives you that expression. Now the second one, you copy y and you multiply times the derivative of this term. The derivative of this term you can verify is this just by the chain rule. You do the derivative of the exponential is the exponential times the derivative of the exponent. The derivative of the exponent is going to give you p of x, and then you just copy the exponential and copy y. So this is your second term of your product rule. So you get a perfect derivative here. You get just straight up one derivative. So when you integrate it, the antiderivative of the derivative just gives you the original function plus some constant phi. And then you get that this is going to be equal to e to the integral of p of x dx, q of x. So now, if you're able to integrate here, the x, that goes away, and if you're able to integrate this one, or find an antiderivative, you get a solution. And in fact, you don't even have to get an explicit form. You can just solve here and just write that y is going to be this term divided by e to the integral of p of x dx. So you can actually find a solution even if you're not able to compute your antiderivative. And I noticed that this got caught up, but I think that when I said it made sense. Why am I starting to write so far to the right? I think it's the light. I'm gonna blame it on that. I have all this not wasted space. Oh well. So whenever I solve an example, I'm gonna start here. All right, so let's go ahead and do that. Let's look at how this expression or how this method works in practice. So let's go ahead and erase and start with one problem. So p of x would be this right here, 1 over x. So the first thing I'm going to do is compute that integral of p of x dx, which is what I need for my integrating factor. So it's going to be the integral of 1 over x dx, which is going to be the natural log of the absolute value of x. I'm going to leave right now the plus c away because it's not needed for this method. Because whenever I solve it, I'm not going to use it. I want to do the constant at the very end. So I'm going to go ahead and do e to this, e to the natural log of x, and I'm going to get that the integrating factor is going to be equal to actually the absolute value of x. So technically I have to separate it into positive, negative, and separate it out. But for right now, let me be very, very informal. I want to multiply the whole expression or the whole equation times x, and it's actually going to work out. So because if you notice, when I multiply just times x, this one right here cancels, and I get what I needed, that this right here is the differential of x, or sorry, the derivative rather, of x times y. If you do, if this is a differentiation like you normally would, you get that expression right there, and that's going to be equal to x cubed. So you see, I didn't really have to worry about my absolute value, cheating, but it worked out. So nobody will disagree with that. All right, so you integrate on both sides here, and you get xy for the left, because this is a derivative. Take the antiderivative, you get xy, and then you get x to the 4th over 4 for this one, and both of them would give you a constant, so collect it here as c. And then you can solve for y as x dividing term by x. So I'm going to have x cubed over 3, 4. I'm so used to saying 3 because of the integral. It just came out automatically. And then set c over x, and that right there gives you your solution. Now, if you had some initial conditions, then you would go ahead and plug them in and find your value of c. So again, as before, I'm going to grab my p of x and I'm going to compute the integral. The antiderivative or indefinite integral, whatever you want to call it. And this will give you the natural log of the sine. Normally you write the negative natural log of the cosecant, but then you put the negative inside, which is natural log of the sine. And the derivative, if you want to check it by chain rule, the derivative of natural log is 1 over u times u prime, u being the sine of it, so you get 1 over sine, times the derivative of sine, which is the cosine, cosine over sine, cotangent. Perfect. All right, so now you do the integrating factor, and you get e to the integral of the natural log. Wait, what? E to the integral of p of x dx. This is integral p of x dx. This is going to be e to the natural log of sine, which is going to give you the sine. Again, I'm going to not use the absolute values. I'm going to cheat, and you already see what's going to happen. So let's go ahead and multiply everything times the sine, and I get sine xy plus, now cotangent is cosine over sine. When I multiply times sine, the signs cancel, and I get just cosine x y equals x squared. Am I out of space? Yeah. X squared and then sine of x. I was so happy that I got extra space, and then I did it. Oh well, good enough. And I'm gonna write smaller. So here you notice that this is gonna be equal to this should be a y prime, right? Yeah. It was y prime. Forgot about it. And so this is going to be sine x y prime equals x squared sine x. So I have to integrate here, and I just get sine x y equals, and I have to integrate this one, and I put it here specifically because in the previous video I told you I wanted to do integration by parts, and I wanted to do partial fractions. So, and this is one of those integration by parts where it's much better to do it with tabular method than to do it by hand. So I want to go ahead and remind you of tabular method so you are so you have reviewed that. All right, let me write this part down clear. I'll be right back. All right, so I need the integral of this x squared sine x. So the tabular method, you start putting signs and you alternate them. I don't remember how many you need. Okay. Put your u here and then your dv here. And as you know, for integration by parts, if you have a polynomial, people use that acronym, the LIAT or whatever it is. Polynomials will always be the u, well, for the most part. And then these guys are going to be your dv's. So the antiderivative of the sine is negative cosine. Then you get that the antiderivative of the cosine is sine. Therefore, this gives you negative sine. And this one's going to give you the cosine again. Because cosine antiderivative. Sine is negative cosine, but we have negative, so it becomes that. And then, once you have your table, you do this kind of thing. And you stop when you get to 0, remember? And so you just grab plus, and then you get x squared times negative cosine. So this is going to give you a negative x squared cosine. That's the first term. And I should have collected everything that had a cosine. If I would be smart, I would do that. Okay, next step. And then minus negative, so it's going to be plus. Yeah, that's going to be hard to fit. Oh well. 2x sine x. I already went out. That's a sine x. And then plus 2 cosine. Plus c. So what I'm going to do is I'm going to collect all the terms, and with cosine, all the terms with sine. Then I'm going to divide by the sine. So I'm going to do all that in one step. Not very smart. Do it in 2 steps. Let's see if we get it correctly. So I'm going to have negative. Whoa. Oh, you see what started happening already? Got nervous. Let me erase. Alright, try again. Y is going to be negative x squared plus 2. Now I'm going to have a cosine over sine, cotangent. And then I'm going to have this one, 2x, and then sine over sine, which is going to be that. Done. And don't forget your c, and when you divide by sine, it's going to give you a cosecant of x. And I ran out of space yet again. So it should be negative x squared plus 2 cotangent of x plus 2x plus c times cosecant of x. And that gives us a solution. Let's do, I said 2 or 3, but I think I'm going to do just one more. 2 nice examples though. I really like them, like this one. I was working on it on my head, and it worked out to be a nice one. So let's do yet another one, and we can wrap it up there. I'll erase and I'll be right back. But let's go ahead and take a look at this one. So the integrating factor would be e to the integral p of x dx. That in this particular case is going to be e to the integral of the cosine x dx. And that's going to be e to the sine x. And the reason why I put this is just so we could cancel it, because once you have to integrate that, good luck. So we get e, but that does highlight the fact that some of these you will just have to leave them indicated. And in practice, you would have to solve them with numerical methods. E to the sine x y, and I'm about to run out of space. I'm going to write the equal. And then when you multiply e to sine x on both sides, you get equal to 1. So then you get that e to sine x times y prime equals 1. So you can integrate, and you get e to sine x y equals x plus c when you integrate, and then multiply times the e to negative that. So we get e to negative sine x, or divide by it if you prefer, x plus c. And that will close our video. But I'll see that I replace the LED strip on my board. So hopefully you'll see a much better quality video next time. But at least you got to see the math. And if you have any questions or any problems that you want me to solve on YouTube, let me know in class or on the comments, whatever you prefer. Thank you for watching, and I'll see you on the next one. So this may be an awkward jump just because I had written an equation that ended up with no antiderivative, and I don't want to have one of those. I worked the whole thing and I'm like, oh, this is one of those. Fail. So I wrote something very, very simple just to close the video, so sorry about that. But let's go ahead and take a look at this one. So the integrating factor would be e to the integral p of x dx. That in this particular case is going to be e to the integral of the cosine x dx, and that's going to be e to the sine x. And the reason why I put this is just so we could cancel it, because once you have to integrate that, good luck. So we get e, but that does highlight the fact that some of these you will just have to leave them indicated, and in practice you would have to solve them with numerical methods. E to the sine x y, and I'm about to run out of space. I'm going to write the equal, and then when you multiply e to sine x on both sides, you get equal to 1. So then you get that e to sine x times y prime equals 1. So you can integrate, and you get e to sine x y equals x plus c when you integrate, and then multiply times then e to negative that. So we get e to negative sine x, or divide by it if you prefer, x plus c. And that will close our video. I endured that thing, well, you endured that because my face probably came in and out of focus. Like there it disappeared. I get a 10. I spent winter, anyways. Terrible joke. But I'll see that I replace the LED strip on my board. So hopefully you'll see a much better quality video next time. But at least you got to see the math. And if you have any questions or any problems that you want me to solve on YouTube, let me know in class or on the comments, whatever you prefer. Thank you for watching, and I'll see you on the next one.